with a short break in the middle. The first speaker will be Tomislav Andrić from GSSI. Will speak about seismic Newtonian noise cancellation for ET. And I stop sharing my desktop so that Tomislav can start preparing.
Ciao.
Hello.
Okay.
Yes, we hear you. Just let me check. We don't see your screen. Tomislav, do you hear us?
Oh, I think he's frozen. Yeah, maybe we should give him a minute to reconnect.
Let's wait just 1 minute, and maybe if the second speaker is already connected, Ina Maria Höhlenbeck.
Yes, I'm already here.
Okay, just let's give 1 minute to Tomislav, and then if he's not able to reconnect, we might start with your talk.
Yep.
He was there.
Yeah, he was there until he started sharing the screen.
Yeah.
Everything went.
That's right. Okay, since looks like Tomislav needs some more time, let's start with the second speaker in the agenda, Ina Maria Höhlenbeck. She's going to speak about low frequency noise mitigation by inter-platform control.
Yeah, thank you for the introduction. Exactly, so I would like to present some slides on low frequency noise mitigation by inter-platform control, and Connor already raised the topic yesterday in his talk, and therefore I have brought a similar slide to what he has already shown. So on the left, you can see a plot that basically summarizes what we have to achieve if we want to go from a second generation to the third generation of gravitational wave detectors. And we see in red the Virgo sensitivity, in blue the LIGO sensitivity, and in black the ET design sensitivity. So this part is mainly about ET low frequency. And these arrows indicate what we have to achieve if we actually want to achieve a very good seismic isolation in a few hertz band. And in this region where we want to have already sensitivity to measure gravitational waves at a few hertz, we need to lower this noise by actually 6 orders of magnitude. And this is, of course, not simply done. So therefore, we need to take some additional measures, and we will use for the seismic isolation in the gravitational wave band the super attenuator, or rather an adapted version of this one. And this is theoretically sufficient to do the tasks, but we already have seen in current gravitational wave detectors, but that actually not the seismic isolation is limiting the detector bandwidth, but rather control noises from auxiliary control loops and also scattered light. So what we think would be a good thing to do to actually achieve the goal is to introduce active isolation below the suspension resonances. So therefore, I brought a slide that is from a different talk by Brian Lenz that he gave during the last LBK meeting. And this raises already this issue at the LIGO detector. So you can see what the LIGO detector is limited by in this red curve. And down here, buried in all these lines, you can see the actual quantum noise limited sensitivity. But what you can also see is that many other noise sources are actually limiting. And one of this is this dark red line, are the alignment control noises. And if we go back to what we will have for the Einstein telescope, we have the modified super attenuator. So this is a picture of the current super attenuator in Virgo. And just a brief recap. So down here we have the mirror, and then we have a chain of isolation systems of mechanical filters and pendulum wires, isolating it from the suspension point motion. So this suspension point is here in the upper part, and on the top we already have an active alignment stage, which is called so filter 0. And there we have sensors as well as actuators to do position control and also some inertial control. The problem there is if we go to an underground site and we have this much lower input noise, which is great, then the sensitivity of our sensors needs to scale with it. And if we then have a look into the interferometer, what's actually important for the interferometer is not necessarily the inertial control below the suspension resonances, but rather the differential interferometer displacement. So in principle, we don't need to reduce the inertial isolation. We could also just reduce the differential motion. And there we can, in principle, use the interferometer signal, but we can only use the signal during operation when the interferometer is in log. So ideally, we would have an additional sensor that measures this differential displacement of the suspension points. And if we go back to our super attenuator and the design of ET, we see that we have the input and output test masses suspended by these long chains. So the suspension point is somewhat high above the mirror. And since we are in an underground site, we don't have a clear line of view because we simply have a lot of rock in between. So in principle, we could go down the super attenuator and then install a periscope, but then we hit a few other problems like the cryogenic shield that will be then in the way. And because of this long lever of the super attenuator, we also require tilt readout. But tilt readout we would like to have in any case. So we would like to also stabilize the angular degrees of freedom to reduce the control bandwidth on the angular interferometer control loops. So what we instead could do is introduce a platform that is actually supporting the whole suspension structure. And if we have a look in the central cavern, we see that we have many more of these tall suspensions. And in principle, we would like to stabilize all suspension points relative to each other. So we would, for example, start at an input test mass and then consecutively go down the beamline and also stabilize the folding periscopes as well as beam splitter, power and signal recycling mirrors, maybe even the mode cleaners, the filter cavities, and so on. So instead of additionally installing tubes to have access to the suspension points, we could also there introduce platforms that would be then on the beam level already. So if we go further down the beam line, we see that we have many auxiliary benches that house the input-output optics. And we have already seen there that large DC drifts between these benches and the interferometer optics often create problems, also with scattered light and these large dynamic ranges. And stabilization of also these platforms would be therefore quite beneficial. So what we would like to propose is that we have seismic platforms close to the beamline and then stabilize all these platforms relative to each other, both in length and in angle. And to demonstrate you that this has been done before already, I have brought this slide from the AEI 10-meter prototype. It's a facility, a large facility that is similar to gravitational wave detectors because it's designed to do prototyping for them. And you can see in the bottom a picture of the vacuum vessel. And in the top left corner, you can see what's inside this vacuum vessel. We have 3 large tanks, and in each there is a seismic attenuation system, which we call AEI SAS. This is similar to Virgo's EIB SAS. It consists of an optical table here where all the suspensions are placed on. And in the lower parts, there are the filter stages. And we use passive filtering with inverted pendulum legs, as well as geometric anti-spring filters. And then additionally, we have active control with inertial and position sensors. And we use geophones and accelerometers as inertial sensors. So what we have done in this prototype is we have used an interferometer that runs in between these 2 platforms. And we use the signal that we get from the interferometer to then stabilize the platforms relative to each other. And this is what is also shown in the graph on the right. So if we have the platforms relative motion measured by this interferometer, we get this blue line. It looks a lot what you would expect from the seismic noise that we also have seen in gravitational wave detectors. And if we then apply this active feedback and let the second table follow the first one, then we can reduce this differential length noise very efficiently, even get down to 10 picometers per square root hertz. So, but as we probably all know, a suspension platform on which the suspension stages are placed doesn't mean that it's quiet at the suspension top, where it's typically suspended from, so at the suspension point. And this is to a very simple fact that we basically have very long levers for our suspension points. So all the tilts couple to these suspension points, and therefore also to the length change of the suspended optics. So therefore we have introduced a system of optical levers and use them to stabilize the tilts of the 2 tables. And if we then have a look at one of our suspended interferometers, in this case it's cavity, which runs in between 2 tables. And we use this cavity basically as a sensor for our suspension point motion, because the cavity imprints its length noise onto the laser frequency, and an additional mode cleaner is then used as an out-of-loop sensor for this cavity motion that's imprinted onto the laser light. And if we have a look there, then we see that we also can transfer this stability to the suspension point. This is shown on this blue curve here, where we can see if we only have inertial isolation from our inertial sensors, we can improve this noise actually by 3 orders of magnitude. So we were able to demonstrate that such a platform stabilization can in principle work. And for our working group, we need some information basically to design such a optical sensor array to efficiently actually apply feedback to the suspension points. And therefore, we need to know the geometry and the sensor and actuator position, which of course then means that we will work closely with other groups, mainly the suspension group. So this is already my last slide. And this is where I would like to talk to you about what we want to achieve if we have such isolated platforms. And this is here at the low frequency range. We would like to help with the active stabilization, the log acquisition, and also reduce the dynamic range, the interferometer signal, and this mid frequencies where the microseismic peak usually occurs. There our optical sensors have their peak signal to noise ratio, and we hope that we can then there efficiently reduce the seismic noise. And in the region where then the super attenuator passive isolation takes over, there we hope that we reduce all these excess noises from the auxiliary control loops as well as the stray light. And at even higher frequencies, we hope that the angular interferometer control bandwidth loops can be reduced, and due to the lower input motion into these stabilization loops. Yes, and as I already said, this was mainly focused now for ETLF, but all these technologies are then in principle just as well adaptable to the ETHF. Yeah, thank you.
Thank you. Very interesting, actually. We have time for a few questions.
Yes, please.
Here, Lino, I would like to know where is the unity gain on your control system, up to which frequency you are controlling?
Yeah, so if we go back to slide number 10, then we see that we have actually not very high control unity gain frequencies. It's in the few hertz region, both for the length and the angular degrees of freedom. This strongly depends on the system you are actually then working on. So if you're if you have a very slow reactive
of course, because here I see also some excess noise.
Yes, yes, we also imprint some excess noise. In this measurement, we really wanted to demonstrate that in principle we can stabilize
at very low frequency, yes.
Yeah, at very low frequencies, exactly.
Yeah, okay, thank you.
Any more questions or comments?
I have a comment,
Go on,
Luca.
Sure.
I switch on also the video.
Yeah,
yes, I have a comment. Hello to everybody. And I mean, in Virgo, we have in use a relative control between the suspension. I mean, I think since probably 15 years.
Yeah.
And it's quite strange, I mean, looking at this kind of activities. So I mean, it's not, I mean, of course, I mean, very nice job, very nice thing, but it looks sort of little bit updated. I mean, I don't know. I think I have the impression that there is no communication between the Virgo community and your group. I mean, that's the
I have to admit it's sometimes difficult, even in our like medium-sized collaboration, to do some efficient communication. I'm aware that there is already feedback that is been used to offload the interferometer signal to this filter zero stage. The question we would like to address is also, is such a system relevant during log acquisition? So there you, of course, can only use the interferometer signal.
Yeah, that's true. I mean, there are several things that one thing that I can understand is that the number of publication is really too limited. I mean, what Virgo is writing is far from being enough. But I mean, the knowledge of a lot of details like this. I mean, of course, we do not use any. For example, we do not use any kind of discharge, let's say, before locking acquisition. But in the past, for example, we implement, and then we decided not to use, but we study and implement a system for automatically compensate tidal movement along the 3 kilometers. I mean, meaning the two super attenuators at 3 kilometers, one from the other, were following a sort of trajectory using data, relative position data when available, and using a tidal movement model when the interferometer was not locked. But at the end, this was never used because not, let's say, not important, not relevant. We have a lot of dynamic, and so we do not need for Virgo that kind of implementation. But at least was studied and was taken up to a really advanced point. We have this system we call GIPSY. I don't know if, for sure, some of you all probably could have heard about that. That is used for increasing robustness during earthquakes. That simply replace the local reference on one super attenuator with the information coming from another super attenuator located 3 kilometers away. I mean, there are, I think, dozens of examples like this. So, but of course, I'm not making any criticize to your talk at all. I insist saying that your job is really great. The question is more for the organization of ET, meaning try to understand how we can involve the Virgo know-how in the AT design. And this needs
if I may comment on this.
Point.
If I may comment on this, this is going to be one of the tasks, one of the main tasks actually of the ISB, of the Instrument Science Board, where people coming from Virgo, from LIGO, from other groups are together and, should.
Yeah, I think also the communication to the Virgo group is extremely important, especially because there has been years and years of data and knowledge that has been accumulated about the whole super attenuator system. This is definitely something we need to and want to look into and hope to get a lot of input actually. So I encourage everyone to contribute with their knowledge into the general AT project, but also into potential platform stabilization. So yeah.
Of course, the key point is that, I mean, there is really a sort of hidden treasure in Virgo. Hidden because really the number of people involved in the activities were always too few, and producing publication for our group in that period at least was not considered as a priority activity, and that was a mistake. Of course, I'm the first to say it was a big mistake, but I mean, things went like that. And so the point is now try to understand what's the best way for extracting the information that is really huge.
Especially at the point of this ET project where you still have design freedom, where you can actually implement something additional that would have been beneficial also for, in principle, the Virgo detector. So I think it's really about addressing the questions, where do we need some additional hardware to fully get to the point
sorry to interrupt, but we need to move on at this point. I think that the point was made very clear, and we definitely should work in this direction. I totally agree. There was a raised hand. I saw it in the chat, but I don't see it anymore. So if there are no more questions, I think we should move on at this point. Thank you again, Sina. Thank you very much for your talk.
Yeah, thank you.
And Tomislav is connected again, so let's give another try.
Yes, let's try again. I hope now it will work. Okay, I can share. Perfect. You see?
Yes, very well.
Okay, perfect. I can start?
Sure, you can go.
Okay, good afternoon, everyone. I am Tomislav Andrić, and I'll talk about seismic Newtonian noise cancellation for the Einstein telescope. So first, I will give you a broader picture about the idea we have, how to have Bayesian seismic array design. Then the most of my talk will be focused on the paper that we published recently, that is about the effects of topographic scattering on the seismic cross correlations and gravity displacement correlations. Then I'll tell you briefly about observation of seismic correlation, and then about Bayesian surrogate model of Wiener filters. So as I said, the beginning, so workflow, we will use numerical simulations. Numerical simulations will provide us prior. And for that, we need to obtain information on geology and topography. Likelihood will be provided by measurement of seismic correlation with seismometer arrays. And then we will use Bayesian surrogate models of Wiener filters for RI optimization in 3D. So just a brief introduction. As you know, seismic Newtonian noise has 3 contributions. The most prominent one is from seismic surface displacement, and that was the contribution that we were taking into account in our simulations. Then there are 2 less prominent contributions that are from compression, decompression of rock and displacement of underground cavern walls. As you can see in this plot on the right, that seismic Newtonian noise is big limitations for low frequencies. So as Professor Harms yesterday was mentioning, seismic Newtonian noise from surface waves at the surface is dominating. So, but as you can see here on this plot, the down, if we go a few hundred meters underground, this contribution decreases. Of course, we will still have to find a solution for body waves. So, as you know, the Einstein telescope is supposed to have triangular shape with arm lengths around 10.7 kilometers. And what we were doing in our investigation is to see the effects of topographic scattering on seismic correlations. The thing about topographic scattering is that it can make seismic field heterogeneous, and then if seismic field is heterogeneous, then the effort and the cost of cancellation system can tremendously increase. You can see that all 3 vertices, so surfaces of all 3 vertices, A1, A2, and A3, these surfaces are 3 times 3 kilometers horizontal dimensions, and below the center of each, the test mass is supposed to be. To build our model, we choose the vertex A3, so surface of around the vertex A3, because it has the roughest surrounding topography, and therefore it has the largest scattering potential. So if we solve problem for vertex A3, there shouldn't be any additional requirements to repeat the analysis for vertices A1 and A2. So what we were doing actually is that we were making models in software Trellis. We were always, which is software for equality mesh generation. We were always performing our simulations on flat and topography models just to see the difference and to see the effects of scattering. And then those models were exported to Spectrum 3D Cartesian software, which is the software for seismic wave, to simulate seismic wave propagation, but it can also do the ambient noise cross-correlation simulations, which we were doing in our investigation, in our research. So models you can see in these upper pictures. One more important step was to have appropriate boundary conditions, and we choose convolutional perfectly matched layers, or CPML. This was an important step since if reflections are very high, they affect our cross correlations, since we were supposed to have semi-infinite medium. So these CPMLs showed to absorb almost all the incident waves. So we can go directly to the results. First measure that we were using is the ratio of autospectral densities is of topographic model case and the flat model case. And that's shown in the plot on the left. So as you can see that topography basically acts as low pass filter. So it scatters out the waves that have frequency approximately higher than 4 Hertz. So in some sense, it shields our test mass for distant sources. What we were doing, we were changing this radius R. Test masses for Einstein telescope are supposed to be protected. So there should be some area in which there are not supposed to be strong sources. So we wanted to see how this changing the radius of this area affects our simulation. Another quantity that we were using to see the scattering effects is seismic coherence, which is just normalized cross-power spectral density. And on the right, you can see for analysis of seismic coherence. With solid lines are the coherences for a flat model. And as you can see that this flat model coherences match pretty well with analytical case, which is just, so seismic coherence in this case is seismic coherence of a flat surface isotropic Rayleigh wave field, which is just Bessel function of zeroth order and first kind. This is expected since our noise forcing was in vertical directions with respect to surface, and it's also the noises were constrained to the surface, and therefore the most of released the seismic waves are Rayleigh waves. Also, you can see that these dashed lines are coherences for topographic case, and as you can see, there are strong deviations from the analytical case. So we can see that scattering strongly affects our cross correlations. Of course, one more thing that could be the reason of deviation is that because of the scattering, we have also mixture of some body wave content. Here in the C plot, we were changing the model size just to confirm that our model is big enough, since since of limited computational resources, we could not go much bigger than 3 × 3 kilometers horizontal dimensions. But of course, in the future, as you can see, the 6 kilometer one basically perfectly matches analytical case. So if we will be able to go sometime in the future for bigger dimensions, for sure that we will do it. So as I was saying at the beginning, this simulated cross correlation will be implemented as priors in Gaussian process regression. And as the final result we obtained, we have seismic correlations and gravity displacement correlations on the top plots. So the right ones, so this one and this one are the analytical cases. And the left plots are the cases obtained from the simulations for A3 vertex model case. So as you can see that the pattern is preserved. Basically, you have the pattern of the seismic circles here, but the symmetry is broken. Also here, you have normalized power spectral density, and it's clear that the topography leaves a clear imprint in form of an inhomogeneity. So as the final result of our research, by this point, we wanted to see where we should place one single seismometer to have the best reduction of Newtonian noise, and this is just Wiener power spectral density of Wiener filter output. Of course, in the future we will have to need like tens of seismometers per one test mass, and the task of optimal positions of those seismometers will be much more difficult. But the basically only information that we need for that is their mutual cross power spectral densities, which are provided by Spectrum 3D. And to conclude with this part, so what you saw that you saw the effects of topography and correlations and Newtonian noise cancellation in the case of one seismometer. This is one important result, but of course we need to include the two remaining contributions in the simulation of seismic correlations. And importance of simulation is that we will only probably have a handful of underground measurements. We will not have enough seismic. We will not have enough measurements at cavern walls. So it will be also very important to have good simulations in the future. So now I go to the second part, that are the observation of seismic correlations.
I have 5 minutes more or less.
Which provides us likelihood for the Gaussian process regression. The instruments that we will for sure have are for our campaigns are Trillium-120. We will also have some 2 Hz geophones. Already at GSSI we have 40 of 5 Hz geophones, which you can see in this plot. How do they look like on this plot on the down left? What we want to do is to have at least 7 days of continuous recording. Maybe it would not be bad like to have 2-3 weeks. Of course, the GSSI will be the part of vertex by vertex site characterization campaigns. And the final configuration of the field is not yet decided. It will be decided once we know which instrument we will have on our disposal. So our simulations define priors for Gaussian process regression. Then we combine them and measure seismic correlations for us Bayesian inference of seismic correlation everywhere in the medium, which forms the basis of the optimization algorithm. This is a crucial step to calculate optimal array configuration for Newtonian noise cancellation. This concept of Bayesian surrogate model of linear filters was introduced in this paper, and also this plot is from this paper. On this plot, you can see a sample of optimal arrays for different frequencies. In this paper, the priors were uniform over the area, but now we will use our simulations as priors. So to summarize, we'll have a Wiener surrogate model that allows us to calculate the Wiener filter for an arbitrary number of seismometers placed at arbitrary locations, which will enable us to calculate optimal sensor locations. So we will be able to have Bayesian design of seismic array, and that way we'll be able to maximize the Newtonian noise cancellation. Important advantages of this are that of course, it can tell us where do we become too model dependent, at which locations we should put other seismometers during site characterization campaigns to achieve a better overall estimate of the field of seismic correlations. Of course, other important things that should be said are that we'll for all this process we will have a great request for computational resources. Of course, we still need to investigate what type of seismic sensors are the best for the most efficient Newtonian noise cancellation. And one more product that the Spectrum 3D Cartesian software gives us, apart from simulated cross correlation, is that it can tell us where should we improve our knowledge of geology. And so those are sensitivity kernels that are shown here. And then summa summarum, that importance of all these processes is that to decrease the required effort and therefore cost of a Newtonian noise mitigation system, and having optimal arrays for the best Newtonian noise reduction, we will be able to increase the low frequency sensitivity of Einstein telescope. And that would be all. Thank you for your attention.
Thank you. Thank you very much, Tomislav. There are a couple of questions in the chat. These are both about the kind of material you're using in your simulation, if the material is homogeneous and lasts.
Yes, it's homogeneous medium. So as we know, in the Sardinia site, mostly granite and schist prevail. So the density of that medium was 2,750 kilograms per meter cube. And velocity, so P wave velocity, we put 3,500 meters per second, and the S wave velocity is 2,000 meters per second, which gives Rayleigh wave velocity around 1,840 meters per second.
Hi, Tomislav. I have a question. Can I ask them?
Yes, sure.
Okay, so first of all, very good work. I like this a lot. So, so there is a R in your slides, right? R 300, R equals 500. So those are basically the distance, how far away you put your sources, right? So you put them in a ring or something.
Yes. That's the radius of source exclusion area.
Okay, and so you see that the farther away the sources go, the lesser the effect of scattering or something?
The impact on that R is not so big, but
okay. So one more question. So with the CPML velocities, so for example, now you have a homogeneous medium. So how would you define the perfectly matched layers? Like, would you exactly put the same velocities as, like, if the medium varies as a function of depth, for example?
Okay.
How would that matter? Like, I know it matters, but like you have to be very clever with it actually, I think. Select the match layers.
Of course, we need more information about geology and then about, of course, the structure of the velocities. But you mean what would be the influence if we have some like higher speeds on deeper layers, or?
Yeah, I mean like different speeds basically. It doesn't matter if it's high or low.
Yeah, I guess there would be some reflections then if there are change in the velocity between two layers, then maybe those reflections also.
No. So what I mean is the PML. So the perfectly matched layer that you put at the boundaries.
Yes.
To absorb artificial reflections.
Yes.
So right now, I think you just put the same velocities for them, right, as the layers, so that they're completely absorbed.
Yes, but I mean, I don't think that the CPML cares much about velocities. I don't know.
No, so how do you do the CPML?
It's basically implemented in the spectrum-3D. It's intrinsically there.
So what are your inputs for the PML?
You just need to define the how many layers or what is the thickness of CPML.
Okay, so only the thickness matters. Okay, that's
yes,
cool.
Yes.
Okay, and now you're doing only with sensors on the surface?
Yeah. Now for the beginning, we only had the sensors on the surface. Yes.
Okay. Did you check how good SpecFM 3D is with caverns? Like if you.
We didn't. We were not still trying to put the sensors. You mean underground on the caverns? No.
No, yeah. I mean just the modeling. Just the modeling. If you just put a vacuum in between, like a circle, like a sphere.
Yeah. We still didn't try, but I think it should be quite fine.
Okay. No, it's very good to know because I would also like to do the same. This is a very excellent approach. And thanks again.
Thank you. Let's take one final question from Peter, please.
Yeah, thank you. I would like to continue. So what is your material? So you can estimate the material attenuation with the difference of dynamic and elastic moduli. Do you think it could be interesting?
Okay, for now we didn't have anisotropy and attenuation are not implemented at all. So.
Yes, I understood. But do you think it could be necessary or not?
Okay, for sure that I know that this attenuation is still okay. Anisotropy we could have implemented, but I'm not sure what the effect would be. But I think for this kind of simulation in Spectrum 3D, I think that it doesn't even support that still the attenuation.
So you cannot implement easily. Yeah, I see.
Yeah, I don't know. Maybe it will be improved, so it can also will support attenuation.
Okay, thank you.
Thank you, Tomislav again.
Thank you.
Let's move on. We now start a series of 3 talks about cryogenics in Einstein telescope. The first speaker will be Lennart Busch from Karlsruhe Institute of Technology, and he will speak about the possibility of using helium-2 in ET.
All right, I just need a permission to share.
You should be able to do that now.
Yeah, thank you. All right, I suppose you can see it.
Absolutely, yes.
All right. Okay, so thank you, Gianluca, and welcome everyone to my talk on helium-2 cooling possibilities for the Einstein telescope. All right, let's get right to it. This figure we've seen a couple of times during the course of this symposium already, but it's also good to show the origin of the motivation for the application of cooling to cryogenic temperatures, because obviously, again, here, if I have my laser pointer, you can see the ETLF sensitivity goal as taken from the conceptual design study. And you have all kinds of noise contributions to that, obviously. And cooling the last stage suspensions influences, of course, the suspension and mirror thermal noise budget.
English, bitte.
Okay. All right, but first, for a better understanding of those, what will the last stage suspensions even look like? And to our knowledge, the most recent information on that is still to use Virgo-like last stage suspensions, which you can see depicted on the left, a model at least. And again, they consist of the marionette, the test mass and recall mass, and in between the suspension fibers. And actually, that marionette suspension fibers and both of the masses together form a pendulum, the evaluation of which is actually the source for the so far estimated suspension thermal noise. The other thermal noise contribution, the mirror thermal noise, originates obviously in the mirror itself. And that can be subdivided into different noise contributions itself again. And here you can actually see all mirror thermal noise contributions for a silicon mirror at 10 Kelvin. And the three most significant contributions are the coating Brownian noise, which we heard a very interesting talk, by the way, of Jessica on today as well, and the substrate thermorefractive noise and the substrate Brownian noise. And for that substrate Brownian noise, we actually found an investigation into kind of the temperature influence at cryogenic temperatures, which was done by Janice Frank and colleagues in 2009. And they simulated the total silicon substrate thermal noise, focusing mainly on the thermoelastic noise and the Brownian noise. And as you can see here, between 10 and 4 Kelvin, you basically have no significant effect of the temperature difference towards the thermal noise. But once you go from 10 Kelvin cross 20 all the way to 30 Kelvin in the substrate, you get an increasing thermal noise growth. And especially in the lower frequency region, just between 20 and 30 Kelvin, the total thermal noise of the substrate increases by about 1 order of magnitude even. So if we use silicon mirrors in the ETLF, we can, at least in the substrate itself, see already a strong cooling motivation in the 10 to 30 Kelvin range. All right, how about the suspensions? Again, a depiction from the conceptual design study. In blue, the ETLF design sensitivity. And the red curve actually is the considered suspension thermal noise, calculated expressing the Virgo-like last stage suspensions that I've just shown to you as a cascade of 3 pendula, the marionette, mirror, and the reaction mass. And actually the dashed green curve there would be the thermal noise contribution by a simple pendulum. And the parameters that I found in the conceptual design study that were used to calculate the red curve, you can see on the right-hand side there in the table. It's not important to go into detail on all of these. I just want to draw your attention to the temperature there, where a mirror temperature of 10 Kelvin was assumed, while the marionette was at 2 Kelvin. So again, we're at 10 Kelvin in the mirror there, and that basically makes it obvious or suggests that the design presented in the original or in the conceptual design study implies helium-2 cooling of that marionette, because with helium-2 we could get as low as 2 Kelvin in the marionette. All right, so our first look at this issue was if we can manage to get the marionette down to 2 Kelvin using helium-2, what mirror temperatures would we then end up with? And in order to do that, we started with analytical calculations, and to visualize what we did better for you, I enclosed the model on the left side, a little bit more of a simpler model there for you. Again, we have the marionette mirror with the ears, and in between the suspension fibers, which is going to be the focus on for a little bit. And the properties which I kept constant during those calculations, or during all the calculations that I'm going to show you today, were the fact that we are going to use 4 fibers per mirror with a homogeneously distributed heat flux among them. The fiber length between the marionette and the upper surface of the mirror ears was 2 meters, and the fiber diameter was 3 millimeters large, which was actually, those were the same parameters as in the conceptual design study again. And the material for both the fibers and the mirror was the same, either silicon or sapphire, with the thermal conductivity dependent on the temperature. And the variables that I'll present in the course of this talk were the total heat load on the mirror and the marionette temperature. So now, obviously, if you have the cold marionette with a heat load going into the mirror, you'll end up with a temperature gradient along the fibers. And a plot of these gradients for silicon fibers along the length of those fibers at 3 different total mirror heat loads looks like this. We have 1.5 watts, 1 watt, and 0.5 watts. And if you now look at the cold end, or close to the cold end there, you're going to notice that there's obviously the largest temperature gradient there, and it kind of flattens out as you go closer to the mirror. And that can just simply be explained by looking at the thermal conductivity of silicon, which peaks at around 25 Kelvin, and in the 10 Kelvin range, you have a rapid decrease of it. If you now look at the end of those curves where we have the mirror, you have the fiber warm end temperature. And if you think about it, that is the same as the minimum temperature that we could reach in the mirror. And I listed those 3 temperatures for you there. And for the helium-2 cooling of the marionette to 2 Kelvin, for the 3 heat loads again. And as you can see immediately in that row here, if we use 4 fibers with a 3 millimeter diameter and 2 meter length, we'll not be able to reach the 10 Kelvin mirror temperature, not even when going as low basically as we can with helium-2 cooling. So what we then did was we varied the marionette temperature between 2 and 22 Kelvin, and looked every time what a mirror temperature we could reach with that. Again, for just exemplary 3 different total heat loads on the mirror. And if you look at 2, 10, and 20 Kelvin, for example, we'll list that for you again. You'll see that between marionette temperatures of 2 and 10 Kelvin, you only have a slight difference in the mirror temperature that you could reach, whereas once you go all the way up to 20 Kelvin in the marionette, you'll end up with the mirror even at a temperature even higher than 30 Kelvin. And I also wanted to include the feasibility of achieving those temperatures here. That's why I inserted the cooling technology at the bottom there.
You have 5 minutes, Leonard.
Yes, thank you. And reaching values close to 2 Kelvin with helium-2 capillaries is definitely a realistic scenario when we would have the helium-2 stationary and capillaries going all the way to the marionette. But I inserted a question mark there for the cryocoolers in 10 Kelvin, because reaching even only, say, 10 Kelvin at the marionette using those long thermal links is already a big challenge, what our colleagues from CAGRA can possibly confirm. And as you see in those plots, from 10 Kelvin on, you end up with progressively increasing mirror temperatures. So reaching 10 Kelvin at least seems to be important. Obviously, it would be better to aim lower than that. The other thing is that it's surely also sensible to take into account that with a marionette at 2 Kelvin, you'll also end up with lower temperatures along the fibers and the possibility of reducing their thermal noise contribution. Okay, so now that we reached basically the end of the fibers, let's look at the mirror itself. And we investigated the temperature distributions in the substrate using numerical simulations with the model that you can see there. We have the substrate, no coating included, and the ears we just assume to be black box cuboids in this case. And on top of those, we had circular areas where we set the fiber warm and temperatures that we just calculated with the analytical calculations at constant values there. And the total heat load we inserted into the mirror coming from one phase as if it were to be absorbed by a laser with a 9 centimeter beam radius. So one of those solutions you can see here in the substrate, and that is for a marionette temperature, again at helium-2 temperature of 2 Kelvin. And as you can see already in the resolution that I had to give you here, how low the temperature gradients in the substrate are. And those were 3 or around 3 millikelvin for a total power of or heat load of 1 watt. And that even only slightly increased when going all the way up with the marionette temperature to 20 Kelvin, which is because we always end up close to being around the thermoconductivity peak there. Okay, so in the mirror, we expect to be above 24 Kelvin. So then we thought, like, can we get any lower than that without using additional thermal links to withdraw the heat from the mirror? And a possible solution would be to introduce hollow fibers that are filled with helium-2. And that hollow length wouldn't even need to go throughout the whole fiber. In fact, we could set the length of the fiber that we want to be at helium-2 temperature more or less freely, and only below that point where it gets massive again, the fibers, we would have a temperature gradient inside the fibers. So that way we could choose the temperatures in the fibers and in the mirror as well, between the 2 and around 24 Kelvin. And obviously that might come in handy because it's those temperatures and more, such as the coating temperature and the suspension temperature, and also the pressure that the cryopumps will provide that are important parameters for us. And it's important for us to gain information on that influence of those parameters on the sensitivity, because currently we obviously don't have the whole picture of these influences. And if we had that information, we could evaluate concepts that we come up with against that ET-LF sensitivity and engineer and propose an adequate cooling system design for the technical design report. But I want to point out, though, that independently from that, we're going to continue the investigation on the helium-2 cooling system design within my PhD in several steps. The first one being coming up with the conceptual design of a cooling system that can provide helium-2, as I said, in capillaries all the way down to the marionette. And once we know enough about those systems parameters, we can and we will need to model the noise propagation in stationary helium-2 to gain experience on how much noise we can expect the helium capillaries to introduce to the marionette. Obviously, the concept we developed that way will need to be proven, and in order to do that, hopefully still within my PhD thesis, we'll develop an experimental concept to assess this then hopefully ultra low noise cooling system. And in the end, I hope we hope that the experiment installation and the proof of concept could be conducted in collaboration with ET Pathfinder, for example, or the IP2L in Lyon. All right, then I can only thank you for your attention, and obviously I'm available for your questions.
Thank you very much, Leonard. Actually, there are a few questions in the chat. Let me see if I can keep track of them. So the first one is from Odio. He was asking, what temperature are you assuming for your inner shield surrounding the mirrors?
Yeah, that was not taken into account yet. The only thing.
So you had no shield around the mirrors in the simulations?
No, I mean, so we didn't consider the radiation yet in our calculations, but we assumed them to be, say, negligibly small against the heat load, including the safety margin that we took from Fulvio, which he also presented yesterday, that 1 watt, especially if you have the cold recoil mass around the mirrors as well.
Yeah. There are a couple of questions from Paula. Maybe Paula, can you speak up? Yeah.
Yes, my first question is about slide 6 you have shown.
Yeah, give me a second.
Where you show the plot of the last calculation in the older conceptual design, and
should be that one, right? Yeah.
Yes, and here is not written that it refers to the low frequency interferometer, so the power which is assumed to be absorbed from the mass is about 18 milliwatts. And so this is the difference from what you have calculated in the in your results and in your slide that you show in your slide 8, where you, if I well understand, you have written that the power absorbed by the mirror is from 1 watt.
500 milliwatts to 1.5 watt.
Yes, so those, if I understood you correctly, was 18 or 80 milliwatts.
18.
Yeah, it's not really important in the milliwatt range. That is without the safety margin, and I mean the safety margin put on top, and then we arrived at 1 watt. We basically came up with in collaboration, or we got that information from Fulvio Ricci's group in Rome.
Yes, I'm from that group. No, I was just referring to what we originally did in that simulation, and we were assuming that the main power which was absorbed was from the coating, and so the coating is assumed to absorb about 1 ppm of the power impinging on the mirror. And we were assuming also about 10 ppm per centimeter for the bulk.
Yeah.
And so that was the result that we got.
Okay. So yeah, I can tell you from my calculations that assuming without that safety margin, you could definitely end up with temperatures around or like below 10 Kelvin in the mirror with 2 Kelvin in the marionette.
Yes.
I didn't include that here because that didn't include the safety margin, which was recommended, but I calculated it anyway.
So, the safety, you mean for safety margin, you mean that you have assumed the 1 watt or
exactly?
Okay. Thank you.
Yeah, no problem.
There are a few questions and comments in the chat. Let's take another one, which might be fast. From Eric, which typical capillary diameter do you have in mind?
In the micrometer range, the largest thermal conductivity that you can get with helium-2 capillaries is around 10 micrometers, so around there.
Okay. We are running a bit late, so I ask you, please, if you can check the chat and maybe
Yes.
answer privately to the other questions. In the meantime, we can move on. Thank you again, Leonard.
Sure. Thank you.
Let's move to the next talk. The next speaker is Piero Rapagnani from University of Rome, La Sapienza, and INFN. Ciao, Piero.
Ciao.
Leonard, you should stop sharing your desktop.
Yeah, I'm trying to. Doesn't give me.
Maybe I can do that.
Yeah, maybe you can kick me out. Doesn't give me the option anymore.
I did it.
Ah, yeah, okay, thanks.
Okay, so I can share my screen, I think.
Sure.
Is it okay?
Yes.
Okay, so I go.
Try to go to screen.
Yes. Okay, so hi to everyone. I'm going to talk about all the other difficulties that we could have in building a cryogenic payload. I am part of the group that has designed and built practically all the cryogenic payloads that have been installed in Virgo since the start, and will be installed in Virgo also in the future. For instance, what we see here is the design of the heavy mass payload with a mirror of 100 kilograms, 105 kilograms indeed, that will be installed in Advanced Virgo Plus in the second phase of Advanced Virgo Plus in 2023, 2024. By the way, this will could be a good starting point also for the heavy mass payloads in ET at high frequency. So now we have this new challenge that the beautiful talk by Leonard has shown how severe is this challenge, because cooling down 200 kilograms mirror with fibers is absolutely not a trivial task. But besides this, what I want to show you is all the other constraints that we have to meet when we do this kind of job, because they're essential. So the cryogenics is something that we must add to a structure that it is sound and that allows to the payload to work as it must work. So we start with, as usual, with the sensitivity and the optical design, the requirements from the optical design to determine the mass, the material, and also the aspect ratio, that is the diameter and the thickness of the mirror. This is very important for the design of the payload. One starts usually from the dimensions of the mirror. And this is an input that it is necessary, that comes out from the, at least a draft optical design of ET, which must tell us which is the, which kind of dimensions for the mirror it is necessary. Now we are using something which is of the order of half a meter. We have already suspended the mirrors of that dimension in Virgo, but it is clear that, for instance, if these dimensions grow larger, then everything must be thought again, considered again. For instance, this is what happened between Virgo Plus in 2010 and then Advanced Virgo, which is currently functioning, is working. And we passed from the scheme where we have the marionette, as has been shown by Leonard and the reaction mass, which surrounds the mirror, to a structure which was more complex with a cage that was attached to the last filter of the suspension chain of the super attenuator, and then acted directly both on the marionette and on the mirror. This was necessary because we had some very, very large, heavy ancillary structures surrounding the mirrors, that were the thermal compensation system and the baffles that were very large. And Cagra, for instance, to go to what is of interest to us, as another different structure with an intermediate mass, with recoil mass, and a recoil mass around the mirror. The structure of the payload is of paramount importance also for the cryogenics. For instance, we could see if it is possible for a T to have a recoil mass around the mirror very close. That could be helpful, for instance, to have a cool shield very close to the mirror. And also, it is important to understand, for instance, if the space that we need to be cooled down is at the level of the marionette or of, for instance, of the steering filter. What happens in this case is that we increase, of course, this shows that we must consider also the optical scheme that we shall use on the payload. But the point is that the structure of the payload, the scheme that we use for the payload, determines also the space that is needed, the vacuum chamber, or the cryogenic space that we need to be around the payload. And so, for instance, from Advanced Virgo Plus and from Virgo Plus and Advanced Virgo, the vacuum chamber was increased a lot, almost doubled, because we had to change the structure using the cage, let's say. So it could be a good effort to try to see if, for instance, we could keep the steering filters out of the cryogenic space, at least the last one. And this is a study that must be done, finding the scheme of the payload with masses and also moments of inertia, and the length of the suspension. And this is a study that must be done by, of course, the working group, which will design the first scheme of the low frequency payload for ET, together, of course, with the cryogenic group, with the group that needs to study the cryogenics, because there are constraints on the dynamics that we need for the payload, and we should see if it is possible to find the trade-off of these constraints with what is best for the cryogenics. After the scheme is found, is designed, the first check that one does, as Leonard has shown, is to check if the new dynamic scheme is compatible with the thermal noise that you expect. Because we have pendulum resonances around, the dynamics could be rather complex, and these pendulum modes could somehow increase the thermal noise that we see, also at frequencies that we use for detection. This is the standard check that we do, and this is, for instance, an example that we have studied during the Advanced Virgo design. And it is essential, besides what the cryogenics require, let's say, because the thermal noise is the most important feature that we must present. Then also there is the control noise, as I already said. The control noise depends on the kind of strategy that we use to control the marionetta and the mirror, mainly, or all the bodies, all the suspended bodies of the payload. This strategy must be performed without increasing the overall noise without affecting the sensitivity of the instrument, with sensors and actuators that have intrinsic noises that are good enough. Also, here is the necessity, the verification of the strategy for the locking and for acquiring the locking and keeping the locking of the entire interferometer. The actuation that is foreseen for the payload must be compatible with the locking strategy that is thought for the entire interferometer. After all these aspects, we have a scheme, only a scheme, it is not the design, of the payload, and this scheme can be used to start the design, let's say. And the design, the first step of the design is to make it
5 minutes, Piero.
Okay, is to make it compatible with the monolithic suspensions. For instance, this is the monolithic suspensions in the advanced Virgo. This is very critical part because the thermal noise is affected by that. And the thermal noise, as I said, is the main point that must be preserved. Of course, as you know, there could be problems with this kind of fibers that are heavily stressed. And this means that the safety must be included in all these aspects. Then, if we go to cryogenics, at this point, having the entire scheme of the payload, we can see which kind of links we must use to cool it down. Whatever we use, for instance, even capillary with superfluid helium, these links must not degrade the thermal noise. And this must be tested on real size models, because the masses, the thermal noise could be affected by the dissipation. The dissipation are heavily affected by the mass that indeed we use to make the pendulum and the kind of suspensions. So this is, for instance, the scheme that could be used for ET. So what we are going in Rome to do, we are preparing a lab to test a real size payload once the scheme has been provided, has been found, and we have a tentative scheme of the low frequency payload for ET. This is a lab that has been financed by funds of our Ministry of Instruction, of Education, and we should be ready by the end of September 2021. We plan to use it to make tests on a dummy payload with all the masses and the lengths that should be by the time known. And in the meantime, we are developing, this is the same, the building that will be used. We are developing a pulse tube cooling station, which we plan to use together with the payload, with the cryostat that we are designing, to make tests at low temperature in a reliable and fast way on this real size model of the payload. This is what it looks like, the apparatus. The apparatus is designed, should be in construction. We should start the construction at the beginning of next year. There are the links like they use in Cagra, and there are the suspension like we use in Virgo, and there is a place, a chamber where we can test vibration sensors, actuators, velocity sensors, accelerators, and so on. We have already acquired the 2 pulse tube, we have this also. This is a low vibration pulse tube cryostat we use also to test accelerometers, cryogenic accelerometers. We have other two apparatus like this. One is in the laboratory of Gran Sasso, because we have this collaboration now with people from Cuore. And that's it. So this is our program. We plan to use this lab as soon as possible. We want to put our experience together with all the others that is working in the AT working group, and I think that we can be useful. And also, it is important that we try to follow the standard path that we have developed in so many years, because we think that this is the most efficient way to reach a goal that is very difficult. But I think it is feasible with collaboration of everyone. So that's it.
Thank you, Piero.
This is our group, just to tell that, and thank you for your attention.
Sure. Indeed, it's clear from your presentation that the payload, especially the cryogenic payload, is going to be a very complex system itself with a lot of interfaces towards many other systems. Yeah.
Yes, it is a work that, especially at the start, where you must really design from the drawing board, everything must be done all together.
Yeah, yesterday during the discussion, Ettore made a comment, which I think is a sensible comment. He was saying that instead of trying to start from the existing design and put on top of the existing design a cryogenic system, we should start from scratch designing a new payload with the cryogenic system already integrated, which I think.
Yes, I think this is correct. What I would like to say is that it would be good to make such design from scratch with the perspective of what is the past experience both in cryogenics and for the design of payloads. Okay, and this is in a sense what I was saying. We can, of course, there is people in my group, in our groups, that has passed a lot of time with this kind of problems, and I think they have a perspective of what it is necessary. Then, of course, we must discuss with everyone to develop things, but the starting point should be, in any case, our experience, not our schemes, but our experience.
Sure. Any more questions for Piero? Okay, if this is not the case, we can stop the session right now and have a short break and reconvene at 40 minutes past 4 o'clock. So in 18 minutes from now.